Thank you, Sanjay, for the introduction. And I'm really happy talking here. Okay. So anyway, well, this- so first let me set some notations. Uh, so K is always for me number field. It's actually finite extension of Q. And OK is actually the integral closure of Z in K. So essentially it is exactly set of all alpha belongs to K such that the minimal polynomial of alpha belongs to Z of X. And let me consider, let me define IK to be set of all fractional ideals So when I say fractional ideals, it is just finitely generated modules over OK contained in K. Essentially, they will be of the form where this alpha i's are coming from K. So these are actually fractional ideals. So if you have difficulty thinking about fractional ideals, like just take Z and Q. So the here in this case, the fractional ideals will be of like n and n inverse kind of. These are like extra things coming up here. Yeah. Mostly you can even think of it as ideals. I don't mind, but yeah. But the only then if it PK is actually set of all principal fractional ideals. And it see we know that set of all there is an ideal multiplication. So the IK forms a group with respect to ideal multiplication, and PK actually happens to be its subgroup. And if I take a quotient group, this is actually well-known object. It is called class group of a number field T. Okay. So it is very celebrated. It was celebrated that when they proved this class group is cyclic, sorry, it is finite. And since ideal multiplication is commutative, it's actually finite abelian group. This is something I want to make note. Yeah. Fine. So, but now, what if class group is trivial? So this is exactly is what I'm saying is actually is that all ideals are actually principal. This implies that K is OK is PID. So in some sense, class group is a measure of how far the OK being PID is. Yeah, this is something I want to make. Okay, so then maybe Euclidean domains. Okay, so what is Euclidean domain? If R is a integral domain, if there is Euclidean function on R, then we call it R is a Euclidean domain. What is Euclidean function? If there is a function, maybe P from R to n union 0, like given any alpha beta not equal to 0 belongs to R, there should be y belongs to R such that P of alpha minus beta y is less than P of beta. If you have such function, then we call it Euclidean domain. But we know if R is a Euclidean domain, I just write ED, then we know it is PA. Okay. So, but question is the converse true? And we know it is not true on the the one example is, I think it is Z adjoint minus 19. This is like the well-known example of PID, but it's not ED. Okay, and actually the thing is almost all PIDs are actually ED. I mean that is what is believed, because let me just state the theorem. It is proved by Weinberg. He proved that if there are infinitely many units in OK, essentially what I say is that rank of OK star is greater than or equal to 1, then OK is ED if and only if the class group is cyclic. So in some sense, other than imaginary quadratic fields, so yeah, I'm sorry, the condition, this is not complete. It's just I have to put one more condition. It is under GRH. Assuming GRH, this is true. So what it says is under GRH, other than imaginary quadratic fields, all other number fields, the OK is PID if and only if it is ED. So there are maybe I should mention some results in the where they're removing the Euclidean domains without GRH. So these are not the complete list, but these are some works to be mentioned. That is, one is Murthy and Harper. They actually what they produce, if OK star, the rank of OK star is greater than or equal to 4, they prove that OK is ED if and only if it is cyclic. And there is Murthy and Clark. So they actually dealt with totally real fields. And some more results to mention. Srinivas. Subramanian. This. They dealt with quadratic fields. I think there's Murthy as well here. Okay, contain the infinite domain. So, okay, is an infinite domain, then it's PID, then class group is 0, but 0 is complete. Okay, sorry, I meant to say no, yeah, it's no, it is okay is PID. If not, that's actually the statement I meant. I think I was good. This is the statement, yeah. Maybe, yeah. Yeah, Srinivas and Subramani. They dealt with cyclic cubic fields. And this, yeah, these are probably two lists on. And the same people with one more person. Only they're bipolar. These are some like recent results and towards proving that it is like OK is PID if and only if it is ED, without the assumption of GRH. But I'm not actually going to present something about this, but something generalization of Euclidean domain. But if you see here, if I have a Euclidean function, then automatically it becomes a principal PID, and I can see this function as also function in some sense, the function on IK. I can still see this as a function of ik to n. But the question is, suppose if my R is not PID, my class group is not trivial, can I still okay, so can I still talk about some function like this? That is exactly. So here comes the Euclidean ideal, that is actually the relation. So what it says is, if I have a function on ideals satisfying something like so given for all, okay, now I want to say C is Euclidean domain, Euclidean ideal. If for every x belongs to IC minus C, there exists a y belongs to C such that phi of x minus y whole inverse IC is less than or equal to psi f. It's something similar to the Euclidean domain, but what it does is something interesting. So once I have a Euclidean, such a Euclidean function on my ideals, then it says something about class group. So when you had a Euclidean when it was Euclidean domain, the class group is cyclic. But when you have Euclidean ideal, then we have if OK has the Euclidean ideal, I'll call it Euclidean ideal class. Okay, Euclidean ideal, then the class group of K is cyclic. So that is what it is. Actually, the Euclidean ideals actually captures the cyclic class groups. Yeah, that's. But now, since we are talking, since I am only talking about ideal, like if C is Euclidean ideal and I belongs to the class of C, then what can you say about I? It is also true that I is also Euclidean. Yeah, the class group class. Yeah. Yeah, I is any ideal. Yeah, every ideal. So C is the one which I fixed. I is fraction ideal. Yeah, C. Yeah. Yeah. This is something, and since every ideal in the class is Euclidean, we call this class itself is Euclidean ideal class. Okay. So now we have seen that if the, yeah, let's go. So as this result, do you also expect something similar to that? Like now, what we have done is, if you have a Euclidean ideals, implies the class group is cyclic. That's good, but is other way is also true? Is another question to ask, and this is exactly what studied by Lenstra. He proved that under GRH, yeah, OK, the rank of OK star is exactly similar to that. OK star is greater than or equal to 1. Then OK has a Euclidean ideal class. If and only if class group is cyclic. Yeah, this is something we have. Yeah, there is at least one. And see here, I actually see one. I forgot to tell. Here I should have some conditions in R. Usually when you see when the definition, they take R to be Dedekind domain. Anyway, there's no problem because our OKs are Dedekind. But truth is, what Lenstra did is Lenstra started with integral domain, and he proved that whenever there's such a function exists, R has to be Dedekind domain. That is so. Yeah, I just wanted to mention that. So let me add this. This is one. So there have been a lot of people trying to remove this assumption of GRH, and I'll probably try to sketch some results. So the first person here again is here one such result. Okay, Euclidean ideals. So first one is actually due to Graves. So what actually what it is proved here is the same. I have that let K be number field, and the rank of OK star is greater than or equal to 1. And if I have the primes P contained in OK and norm of P is less than or equal to X, and this map from OK star to OK factor P star, and one more condition. Yeah, that's also worry about the class, right? I should fix let belongs to class group, and if I count all the primes in this class satisfying these conditions, if it is greater than or equal to x by log x square, then Graves proves that the C has this ideal class C has to be Euclidean ideal class. That is what the Graves proves. So using this result, so mostly I refer to this as a growth lemma. So using this growth lemma, Murthy and Graves proved that. So whenever OK star, the similar thing, rank of OK star is greater than or equal to 4. And yeah, I think I should also mention that K over Q is a Nebelian extension. This is another extra condition they'll have. Then rank of OK star is greater than or equal to 4. He proves that K has a OK has a Euclidean ideal class. Okay. Maybe I'll just quickly sketch the how the proof goes here. So for that, I probably would need something called Artin symbol. Yeah. Yeah, I'll just define. So let L over K be Galois extensions of number field. Okay. And say P be prime of L containing above lies of O. Okay. Okay. And if P is unramified on OL, then there exists a sigma belongs to Galois L over K such that sigma of alpha is congruent to alpha power norm of P mod P. So that is what is something. So now L over K of this is actually called the Artin symbol, and which is actually equal to this sigma. So this one is easy to see because like once I have this P is unramified, then if I consider this map, the map between decomposition group to the art of Galois of the residue fields, it is actually OL over this or OK over this P. So this somehow happens to be isom. 5 minutes. Sure. I'll finish. Okay, so this will be isomorphism. That's okay. Then fine. This is Artin symbol. So why I define Artin symbol is that using Artin symbol, we actually have a map between the class groups and yeah, so Galois group of H of K or K. So this is called Artin map, and so using this here, why I wanted this is because H of K, K, Q. See, we know that once I take K over Q to be abelian, then by Kronecker-Weber theorem, this is the smallest f of smallest f such that is embedded inside this cyclotomic field. Once so I have this. So now this Galois, this H of K is actually the Hilbert class field. So this will be somehow isomorphic to Galois Q zeta F or Q or Gal. Sorry, okay, H of K. So whole point is this is actually this goes something like this will be I can identify this as Q zeta F. Not identify actually, but this is like but I know what this is. This will be like some Z mod F Z star. But I ultimately, so if I take a generator here, that will correspond to some A here, and so whenever this P is isomorphic to that A mod F, then my primes are actually they're going to be they're going to come to such a class. That is what is means that will fall into this criteria. That is what I want to say, and yeah. So now what the problem will transfer to is that actually is like counting a primes over a Q, and that they'll do it using a sieve methods. That's idea of this thing, and then maybe I'll just quickly mention two more results and then I'll finish it. So one other thing is for rank OK star greater than or equal to 3. So this is the result by this way. Charles Gun and then Sivaraman. So here they had one extra assumption and they used for using the error bound, that is actually gal Q zeta F for K is cyclic. That one extra assumption they had to have, and this is mostly is not true in case of biquadratic fields. That is exactly we try to do using the basic examples, and maybe so we actually try to look at biquadratic fields in Q adjoint root Q and root K. So where Q and K and R are congruent to 1 mod. This was done by Hasu, and where they had a Q congruent to 3 mod 4 and other both are, this was Chattopadhyaya and Muthukrishnan. And we proved that whenever if I say one of K or R is congruent to 3 mod 4, and we actually proved that this kind of biquadratic fields like biquadratic Euclidean classes, and we actually use one of the main ingredients was this, and another theorem by Graves, and what we had ultimately we had to use some Chinese remainder theorem to get such a U like what Ramurthy proof they got.